We are given two resistors, R1 and R2, and a battery, V, and asked to connect them. There are two simple ways that we can do this. We can either connect the elements in series or in parallel. For each of those types of connections, the amount of current and voltage across each resistor, hence the power dissipated in each circuit, will be different. The question is, are these circuit parameters for the two circuits related? And if so, how? That is what we shall be finding out in this video. Let's assign some values to those elements. Let R1 be 2 ohms and R2 be 5 ohms and V be 12 volts. What is the value of the voltage and current through the resistors in the respective circuits? Before we proceed, let's familiarize ourselves with the representations and terminologies that will be used throughout. I superscript P subscript I represents the current through resistor I in the parallel circuit. I is a positive integer. ISI is the current through resistor I in the series circuit. VPI is the voltage across resistor I in the parallel circuit. VSI is the voltage across resistor I in the series circuit. I superscript S is the total current flowing in the series circuit. IP is the total current flowing in the parallel circuit, and V is the supply voltage, which is the same for both circuits. For the series circuit, the current that flows through resistor 1 is given by V over the sum of the resistances. That is 12 over 7, which is 1.714 amperes. This is the same current that will flow through resistor 2, and it is also equal to the total series current. For the parallel circuit, the current through resistor 1 is given by the voltage across resistor 1 divided by R1, which is 12 over 2. This is because when resistors are connected in parallel and then to the supply voltage, the voltage across each of them is equal to the voltage of the supply. So, the current through resistor 1 is equal to 6 amperes. For R2, the current is given by 12 over 5, which is equal to 2.4 amperes. From Kirchhoff's current law, the total parallel current is equal to the sum of the branch currents, which is equal to 8.4 amperes. The voltage drop across resistor 1 in the series circuit is given by the current through it times its resistance. This gives 1.714 times 2, which is equal to 3.4 volts. Likewise, the voltage across R2, which gives 8.57 volts. For the parallel circuit, the voltage across R1 is equal to that across R2, which is equal to the supply voltage. Now, let us take the ratios of these parameters for each resistor. The current through R1 in the parallel circuit divided by the current through R1 in the series circuit is equal to 6 over 1.7, which gives 3.5. Also, the voltage across R1 in the parallel circuit divided by the voltage across R1 in the series circuit is equal to 12 over 3.4, which is equal to 3.5. The ratio of the currents for R2 gives 1.4, and for the voltage gives 1.4. Moreover, the ratio of the total parallel current and the total series current gives 4.9, which is equal to the multiple of 3.5 and 1.4. Rearranging the equations, we have IP1 equal to 3.5 times IS1. Vp1 equal to 3.5 Vs1. Also, Ip2 equal to 1.4 Is2 and Vp2 equal 1.4 Vs2. So in general, we can write Ipi equal to sigma I times Isi and Vpi equal to sigma I times Vsi. For the total current, we have Ip equal to 4.9 Is. We have seen that 4.9 is the multiple of the sigmas of the two resistors. It is also equal to the sum of the sigmas of the two resistors. So we can write Ip equal Is times the product of the sigmas, or Ip equal to Is times the sum of the sigmas of the two resistors. The equation with the product only works for two resistors, but the one with the sum works for any number of resistors, so is the more general form. Let's call sigma the relative multiple. The next question now is, how can we find sigma for any given situation? To answer that, let's refer back to our circuits, but this time we shall analyze them more generally. The current through R1 in the series circuit is given by the supply voltage V over the sum of the resistances of the resistors. This simplifies to V equal R1 plus R2 times IS1. The current through this resistor in the parallel circuit is given as V over its resistance, which when rearranged for V gives V equal to R1 times Ip1. Equating these two equations produces the following equation, and rearranging produces the following green equation for Ip1. By comparing this to the general equation for Ipi, we see that sigma is given by the following equation, and the inverse of the sum of the sigmas is equal to 1. P can be considered as the probability or the extent to which a resistor opposes the flow of current. Let's see how we can apply this to solve circuit problems. Consider our series circuits below. Let R1 be 10 ohms and R2 be 5 ohms. Let's use a 12-volt battery for the supply. What is the voltage drop across each resistor? We start by finding the relative multiples of the resistors. For R1, sigma 1 is given as the sum of the resistances of all the resistors divided by R1. This gives 1.5. For R2, we have 3. Now, we use the voltage relation above, noting that Vpi is the same as the supply voltage. So, for R1, the voltage relation is this, and rearranging for Vs1 gives 12 over 1.5, which is equal to 8 volts. If you do the same thing for R2, you get 4 volts. Calculating the relative multiples is very easy and straightforward, and you don't even need to write down the equation. I wrote them down just so that you can see how it is used. You can verify these results by solving the problem in your own way. Let's take another example. We have 4 resistors connected in parallel as shown, and their corresponding resistances are given as follows. They are connected to a 12-volt battery. What is the total current flowing in the circuit, and hence, what are the individual branch currents? To solve this, once more we need to calculate first the relative multiples of all the resistors. Sigma 1 is given by 29 over 10, which is 2.9. 29 is the sum of the resistances, Following from that, the order relative multiples are given as follows. The total series current is V over sigma Rj. That is the supply voltage over the sum of the resistances, which gives 0.41 amperes. Using our total current formula, the total parallel current is given by the sum of the sigmas, which is 25.6, times the series current, which is 0.41, and this gives us 10.5 amperes. Note that we can combine the two yellow expressions into one equation, which can be used as a shorter formula. To evaluate the branch currents, we use the current relationship as shown, and we get the following results. Summing these values gives a total of 10.5 amperes as before. What I have presented so far is a new alternative way of analyzing electric circuits, which can be easier and more convenient for some people, and even shorter. It also reveals an intriguing relationship that exists between series and parallel circuits, which no one has ever put forth before. However, the true strength of this formalism lies in its ability to yield, in addition to the current and voltage divider roles, the power divider role. Continue to Part B for the derivation.